My name is Carlos Howdegi, and I'm going to be talking about IP fragmentation. So the first subject is frame encapsulation. When a datagram is sent over a network, it's encapsulated or wrapped within a frame that is compatible with that network. When it arrives at the next hop, the receiver unwraps or decapsulates the datagram from the frame, and then the datagram is processed. The datagram is then re-encapsulated into a new frame and sent to the next hop. So one important term is the maximum transmission unit, or the MTU. The MTU is the maximum size of frame data that can be encapsulated in a network. Different networks and protocols may have different MTUs. IP datagrams that are larger than a particular network's MTU are fragmented or broken into chunks. So on the topic of fragmentation, when a router detects that an incoming datagram exceeding the next hop's MTU, it will divide into smaller fragments. Each fragment is an independent datagram that retains all of the original datagram's header fields with a few modifications. Length is adjusted to reflect the length of the fragment. A more fragments flag determines if there are more fragments following the current one. And the fragment offset determines the position of the fragment's data in the original datagram. One thing to note is that the 16-bit identifier remains the same for all fragments of the same datagram to aid in reassembly of fragments. So here's an example problem. Suppose you sent a packet with 5020 byte data payload over a network with a maximum transmission unit of 1600 bytes. Each datagram header is 20 bytes. So the questions I'm going to be answering is, how is the packet fragmented during transmission? I'm also going to describe the size and structure of each fragment, and I am going to calculate the offset of each fragment. So we know that the payload of the original datagram is 5020 bytes. Since the datagram is not fragmented, the fragmentation flag is 0 and there's no offset. So the first step for fragmentation is to find the amount of fragments that we need to send all of the data. To do this, we find the fragment payload size, and we take the total payload of 5020 bytes and divide it by 1580, which is the 1600 byte MTU minus 20 for the header. We take the ceiling to figure out the total amount of packets needed, since we can't have partial packets. So to calculate the size of each fragment, we can assume that all except for the last fragment will be full with 1580 bytes of payload data and 20 header bytes. For the last packet, we can subtract the running total of payload bytes from the original datagram's payload. So in our example, we get 860 bytes of data with a 20 byte header for a total fragment size of 880 bytes. So moving on to the fragmentation flags, the first fragment has its flag set to 1. This is because there are more fragments coming after this one. The same applies to fragments 2 and 3. Both of those fragments have more fragments coming afterwards, So the more fragment flag is set to 1. The last fragment has a value of 0 because it's the last fragment and there's nothing coming after. So moving to the offset section, the offset represents the starting position of the fragment's data as a unit of 8-byte blocks. The first fragment has an offset of 0 because the data is the beginning of the original datagram, so there's no preceding data. For fragment 2, the offset is equal to all of the preceding data divided by 8. So in this case, it's 1580 divided by 8, and we get an offset of 197.5. And that's in a unit of 8-byte blocks. One thing to notice is that we take the floor in our final offset because the offset represents the total amount of complete 8-byte blocks. So in our case, this will be true for any of the fractions we encounter in any of the fragments. For fragment 3, the offset is equal to all preceding data divided by 8, and in this case it is 1580 plus 1580 divided by 8, so we get an offset of 395 8-byte blocks. And then for fragment 4, we follow the same procedure. We take 1580 plus 1580 plus 1580, which represents all of the preceding data, and divide it by 8 to get an offset of 592. So here's problem 1, and you can pause that if you need. And here's problem 2.